Welcome back, logic students. We're going to discuss chapter 3, section 5 today, but I do want to go back for a second to chapter 3, section 4. You'll notice on the syllabus that's not required reading, but what I would like you to do is to turn to page 277 in that section and look at that monster truth table. It's got 208 T's and F's, and on the next page I give an argument that would require 272 T's and F's in a truth table. Obviously, that's very cumbersome and it increases the odds of human error involved in calculating all the T's and F's. So wouldn't it be better if we could develop a method that would do the same thing in a tiny fraction of the number of calculations? That's what chapter 3, section 5 does. So when we turn to chapter 3, section 5, we learn this new method called indirect truth tables. And if you look on page 291, you will see a chart that is going to be your best friend for the rest of the course. That chart will help you learn the method for indirect truth tables and will answer any lingering questions that you have. In section 4, in order to prove that an argument is valid or invalid, you would have to use a full truth table and try to directly prove that that argument is valid. That's the reason why it is so cumbersome. What we develop in section 5 is a truth table method that instead tries to prove that the argument is invalid. And if it can't prove that it's invalid, it's indirectly shown that it's valid. That's why it's called the indirect truth table method. And it will cut down by 90% roughly the number of T's and F's we're going to have to use. I would love to go through all the material in section 5, but under the circumstances you need to read and contemplate that material on your own. What we're going to do instead is to turn to the practice exercises on page 299. I am going to do the odd-numbered ones, and the even-numbered ones will at least have answers in the answer key module on the course page. Okay, we're going to start with easier problems and work to harder ones. Number 1 on page 299 is presented in what we call standard form. What we have here is an argument with the premise above the horizontal line and the conclusion below it. This is how the argument will be presented to you, say on a test or in any of the practice exercises. What we do is to turn it into a truth table by writing all of the premises and conclusion on a single line. And we're going to separate the premises from the conclusion with a double slant bar. So here's the sole premise, and here is the conclusion. Now, in this method, we're going to try and, as I put it maybe unpleasantly, go for the throat. We're going to try and prove that the argument is invalid instead of proving that it's valid. In order to do that, what we want to do is to set the conclusion to be false but the premises set to be true. Going all the way back to chapter 1, what kind of deductive argument is it that has true premises but a false conclusion? It's an invalid deductive argument. So what we're going to do in this method is we are going to set the conclusion to be false. We'll try and make the premises true, And if we can do that consistently, we've shown it's invalid and we're done. If we cannot do that without deriving a contradiction, then we have not been able to prove it's invalid. In other words, we've indirectly shown that it's valid. This will come with practice. Here we have the premise and the conclusion written on a single line. We have created a truth table under it. We're going to leave the double slant bar column blank. What we do initially is to set the conclusion to be false. I'm sure that you've read the book, and so you know that there are only 5 possible kinds of conclusions and only 5 possible ways to set the conclusion to be false. Here we start off with the easiest of the possibilities, where the conclusion is a single letter, B. If we want the conclusion to be false, we make B false. What that means, though, is that for the rest of the argument, we are going to have to set B false every time that we see it. Okay, so let's go to the premise now. Here's the premise, B horseshoe B. The main connective is the horseshoe. If we want the premises to be true, what we want to do is to set that main connective to be true. So we'll make the horseshoe true. Then we'll put in the value of B in these 2 spots. B is false here, and B is false here. Now, does false, horseshoe, false make the horseshoe true? Yes, it does. So what we've done is to consistently assign truth values, making all of the premises true, but the conclusion false. That fits our definition of invalid. So what we've done with this tiny truth table is to prove that this argument is invalid. Let's try another. Let's go to number 3, also on page 299. Here is the argument in standard form. What we have are 2 premises and a conclusion below the horizontal line. What we want to do then is to write the premises and conclusion on a single line, and we'll separate the premises from each other with a single slant bar, and we'll separate the premises from the conclusion with a double slant bar. This will allow us to visually separate these compound propositions. Okay, so we create columns just like we've been doing all through chapter 3 to create a truth table. And we're going to leave the columns for the single and double slant bar blank. Now, again, if you've been reading the book, you know that the simplest situation is when you have a single letter as the conclusion. We want the conclusion to be false. So we set P to be false. And once we do that, we've got to always make sure that P is false. Now, with this method, the virtue of it, but also the confusion about it, is that there is no one single sequence that's the right sequence. You can make up your own sequence as to which of these values you go to next. There's no one right answer. That's explained in the chart that I talked about on page 291. You'll see the truth of that as we continue with the practice exercises. But what I, in general, tell students is the most natural way to do this, since we read from left to right, is to go from left to right, go to the first premise. Here's the first premise, P if and only if D. We want that premise to be true. So we're going to make that triple bar true. Then we're going to insert the value for P that we had in the conclusion. We set the P to be false in the conclusion, it's got to be false from now on. So we're going to put false here for this P. Now what we have to do is think backwards. This is very much like solving a detective story. In fact, this kind of reasoning is the so-called deduction that Sherlock Holmes always used in the novels. If this triple bar is true and the left side is false, what does that force D to be? If the triple bar is true, D has got to be false. False, triple bar, false will give us a true triple bar. So now we've made the first premise true, and we go to the second premise. The second premise is just the letter D. And we need that premise to be true, so we make the D true. But previously, in other words, just a second ago, we said that D is false. So we also have to make this D false. Wait a minute, this D is true and false at the same time. A contradiction. What that means is I cannot consistently assign truth values, making all of the premises true and the conclusion false. I cannot prove that it's invalid, so I've indirectly shown that the argument is valid. Now, surely many of you will think, well, wait a minute, what if I did it in another order, another sequence? That's perfectly all right. What would then happen is that the contradiction would float somewhere else. Let's say instead, we're going to do a second version of this argument right now. Let's say instead that what I did was to set D to be true because it's the premise, the second premise. I start here and then go to the first premise. Well, now I've got a false P, a true D. That would make the triple bar false, but it's got to be true. So now the contradiction occurs here. Or if I set P to be false, the triple bar to be true, then D would have to be true and false at the same time. What you're seeing here is that where the contradiction occurs depends entirely on your sequence, and there is no one right sequence. That means that this technique is as much art as it is science. And it's a lot more fun because it's like trying to figure out a puzzle. It's doing a puzzle, a whodunit. And hopefully that's maybe more enjoyable than some of the other techniques that you've seen so far in the course. Let's continue on to some other practice problems. Let's turn our attention to number 5. Here the argument has one premise, P implies Q, and the conclusion is not both P and not Q. Okay. We create a truth table like we've done before. Columns are obvious. Now, the number of rows depends entirely on the nature of the conclusion. A single letter automatically means one row because there's only one way that a single letter can be false. This one is more complicated. We want this main connective, the tilde, to be false, right? We want to set the conclusion to be false. So we need it to be false. Now we have to think backwards. Previously in chapter 3, we've always calculated forward. Now we have to calculate backwards. This is part of the Sherlock Holmes deduction process. If this tilde is false, what does that mean the dot has to be? Right, it has to be true, because they're always going to be the opposites. The governing connective and a tilde on the outside will always be opposites. So that dot has to be true. Okay, let's think further with Sherlock. If the dot is true, what does that mean P has to be? Right, that P has to be true. And if the dot is true, what does the tilde have to be? Right, it also has to be true. But if not Q is true, what does that mean Q has to be? False. So we've been thinking backwards. It's a whodunit, it's a mystery. Every time you're given one piece of information, one scrap of evidence, and that's that the conclusion is false. Then you think backwards and you reconstruct the entire story from that one piece of evidence. Here we've got now two truth values. We've got P being true and Q being false. This is actually the hardest part of this problem. It's going to be easy from now on. Let's go to the premise, and again, this isn't necessary, it's strictly arbitrary, but for beginners, it's best to go ahead and set that main connective to be true. That way you remember it's supposed to be true, because it's easy to forget. We'll set the main connective of the premise to be true. Now, we insert the value of P from the conclusion. We know that P has to be true all the way across. And we're going to insert the value of Q. Now, we know that Q has to be false because it was false in the conclusion. But look, if that horseshoe is going to be true and the antecedent is true, that forces the Q to be true. But it's also false. So that Q has to be true and false at the same time. We represent that as false slash T or T slash false. It doesn't matter which order. But there's a contradiction. What that means is I cannot consistently assign truth values, making all of the premises true but the conclusion false. I cannot show that it's invalid, so I've indirectly shown that the argument is valid. Another way to put that, and maybe more simply, is that if you get a contradiction on every line in your truth table, the argument's valid. If you get even just one teeny tiny line where there's no contradiction, the argument's invalid. That's also expressed in the chart on page 291. Let's take another one. Let's try number 7 on 300. Here we've got two premises. S implies U, not S, and the conclusion is not U. This is only a little bit more complicated than what we've seen before. What we're going to do is we're going to draw our columns like so, and for purposes of the test on electronic medium, you're already going to have a graph set up for you. The number of rows is determined strictly 100% entirely by the nature of the conclusion. Here what we see is a negated simple statement. The main connective has to be set to be false. Why? Because the entire method is to set the conclusion to be false and the premises true. So we set the conclusion, the main connective of the conclusion, to be false. There is your one piece of evidence. And then you, as the detective logician, reason backwards. If not U is false, U surely has to be true. Now, where do we proceed next? Answer, strictly up to you. You could go here, you could go here, or you could plug in a value for U here. Which one's the right one? There's not a right one. But again, as beginners in this method, what you might want to do is to identify the main connective and set that to be true, so you remember it's supposed to be true, because we're trying to make all of the premises true. Okay, so we're going to make the horseshoe true. We don't know anything about S yet, but from the conclusion, we know that U has to be true. Okay, now does that force anything with the S? If the horseshoe is true and the consequent is true, the S could be true or it could be false. It doesn't force anything, so we'll leave it blank. Okay, what that does though, it means that just with our assignment of U being true, this statement is true. So we've made this premise true. Now let's go to the second premise. Here, obviously, the main connective is that tilde. And we need the premises to be true, so we'll set that tilde to be true. Okay, if not S is true, that means surely S must be false. Have we said anything else about S? No. So we're through with that premise, and what we've done is to consistently assign truth values, making all of the premises true and the conclusion false. And by consistent, I mean no contradictions. So we have shown indirectly that this argument is invalid. There is no contradiction. Now, surely some of you will ask, well, wait a minute. Once I find that S is false over here, do I have to put S is false over here? Answer, no, you don't have to. Next question, can I put the S as false over here? Yes, you can put the S as false over there. Final question, well, if S can be either true or false, don't I have to put this? No, this means true and false at the same time, not true or false. This will become apparent with more practice. Let's go ahead and try another one, and I'll get a little more board space here. Again, since I'm erasing it, I'll just mention to you that that chart on 291 is worth its weight in gold. Go back and consult it until you no longer have to, and you'll do great. Okay, that was number 7 on 300. Let's go to number 9 on 301. This is much taller grass, as I like to put it. It's more of a difficult problem, but it helps us learn the method very effectively. Number 9 has two premises, M if and only if N. It's not the case that N implies M. And then the conclusion is both M and N. Okay, now, what we'll do is to create a truth table. Like we have before. You know how to set up the columns. Now, what determines the number of rows? The number of rows in this technique is always determined by the nature of the conclusion. Here, the conclusion is a dot, and we want that dot to be false. Question, how many different ways can a dot be false? Answer, 3. There are 3 different ways for a dot to be false. So what we're going to do is we're going to set up 3 rows. Good news, we may not need them all. Bad news, we might need them all. But we're going to set them up so we at least remember we might need to check 3 rows. We want that dot to be false. How could that dot be false? If m is true and n is false, or if m is false and n is true, or if m is false and n is false. Those are the 3 possibilities. If we can get a row without any contradiction, we stop and we're done and it's invalid. If we cannot get a row without any contradiction, we have to keep going. And if we get contradictions all the way down to the bottom, then we have to stop and say that it's a valid argument. Let's just go ahead. This is going to be easier than it seems. Let's just take the first row where m is true and n is false. Let's go over to the first premise. The main connective is the triple bar. And remember, we want the premise to be true as part of the method. So we want that triple bar to be true. Go ahead and set it as true so you don't forget. Now, go over and put in the values of m and n. M is true and n is false. Oh my gosh. Well, now what do I do here, you might ask? Do I put the contradiction here that n has to be false and true to make the triple bar true? Yeah, that's okay. You can put the contradiction here. Or you could leave n false and put the contradiction here. That the triple bar has to be true because it's the main connective, and it has to be false because it's true triple bar false. What you're seeing is the location of the contradiction is strictly relative to your sequence, and there is no one right sequence. But what this means, I'm going to just put the contradiction here. What this means is this row is no longer of any help to me. This row will not help me prove that it's invalid, so I don't have to do any of this. But I have to go to the next row because maybe it will invalidate it. So let's go to the next row where m is false and n is true. Let's go back over to the first premise, and again we want to set the main connective to be true. Okay, good enough. And we see that m is false. So let's put in false for m. Well, if that triple bar is true and the m is false, that means that n has to be what? N has to be false. But what did we say it was over here? We said it was true. So it has to be true and false at the same time. Contradiction. What that means is on this row, I cannot consistently assign truth values, making all the premises true and the conclusion false. I cannot use that row to prove it's invalid. But I can't stop and say, well, it's valid because maybe this row will invalidate it. Let's keep going. On this row, m and n are both false. Let's go here to the main connective in the first premise and again assign it to be true. Well, m we said is false, n we said is false. Does false triple bar false give us a true triple bar? Yes, it does. Oh my gosh. This is a different outcome on the first premise, isn't it? We can make that first premise true and the conclusion false. So now we do have to go to the second premise here on the third row and see how that goes. The main connective of the second premise is the tilde, so we're going to set that tilde to be true. Okay, so by detective deduction, if that tilde is true, the horseshoe has got to be the opposite. It's got to be false. What is the only way that a horseshoe can be false? If the antecedent, n, is true and the consequent, m, false. Well, we've said that m is false over here, but we said that n has to be false, and now n has to be true here. So there's a contradiction here. What that means is that there is no way that I can consistently assign truth values making the conclusion false and the premise is true. I cannot prove that it's invalid, and if I can't prove that it's invalid, I've indirectly shown that it's valid. Boom. Again, that chart is priceless to help you because it's going to say when you've got multiple rows, you have to show a contradiction on every row to make it invalid. If there's even just one tiny row out of the three where there's no contradiction, you can stop and say that it's invalid. This is longer looking, but it's not necessarily any more difficult. Let's try number 11 at the top of 302. Here what we have is one premise. Both P implies Q and Q implies P. And the conclusion is P if and only if Q. Okay, now by using a full truth table method, this would be extremely long and cumbersome and unpleasant. The method that I'm teaching you is going to hopefully make it a lot easier. You can set up the columns by now, surely. But what determines the number of rows? The number of rows is determined entirely by the nature of the conclusion. It is a triple bar statement. Question: how many different ways can a triple bar be false? Answer: 2 different ways. So we're going to set up 2 rows. We may not need both of them. Hopefully we won't need both of them. But we're going to set up 2 rows to remind us that there's 2 ways for that triple bar to be false. What are they? Well, if P is true and Q is false, the triple bar is false. Or if P is false and Q is true, the triple bar is false. So those are the 2 possibilities. We'll just take them one at a time. This will go easily, and I think it will also provide something of a surprise to you. On the first row here, we've decided that P is going to be true and Q is going to be false. Now let's go to the sole premise. There are many, many different ways to start this. We could plug in the P values, or we could plug in the Q values, or we could plug in the P and Q values, or what I would suggest to you is going to the main connective, that dot, and setting it to be true, because we want that badly to be true. Now notice here's the surprising little sideline. If that dot is true, thinking backwards, deductively, what does that mean this horseshoe has to be? The horseshoe also has to be true. And what does this horseshoe have to be? It's got to be true because with a true dot, both of the conjuncts have to be true. You can go that route. In any case, let's pursue this particular sequence. If you do it differently, you will surely still get the correct answer. Okay, now, in this first set of parentheses, we've said that the P is true and Q is false. Now, does true horseshoe false give you a true horseshoe? No, it gives you a false horseshoe. So we've got a contradiction right there. If you had done another sequence, you would still get a contradiction. You would still have to get a contradiction, but it could be anywhere. Literally, any of those 7 cells could contain that contradiction, depending on your sequence, and there's not one right answer. So it is a lot of art along with science. But what we conclude from this first line is it's not going to help us prove that the argument is invalid. So we've got to keep going. Maybe this second line will prove that it's invalid. Okay, now let's try the same idea here on the second line. The main connective is the dot. Let's go ahead and make it true. Thinking backwards, reasoning backwards. If that dot is true, that means both of the horseshoes have to be true. That's going to help. Now, let's go to the first set of parentheses and put in the values of P and Q that we learned from the conclusion. We learned in the conclusion that the P needs to be false and the Q true. Does false horseshoe true give you a true horseshoe? Yes. It does. So we continue on. Now let's go over to this set of parentheses. And again, we put in true for Q and false for P. Now, does true horseshoe false give you a true horseshoe? No, it does not. It gives you a false horseshoe. So we've got a contradiction that occurs here. Again, if you used a different sequence, your contradiction could be in any of those 7 spots and it would still be okay. What this shows me, though, is that no matter what, I cannot consistently assign truth values making the premise true and the conclusion false. I cannot prove that it's invalid, and so I've indirectly shown that it's valid. That is a teeny tiny number of T's and F's compared to the monster table that would be required in the full technique. And the more complicated the arguments get, the more efficient and helpful this technique becomes. In fact, when you've got a really complicated argument, this becomes beautiful in its effect. And just a great help. Okay, so that was number 11. Let's try number 13. And again, I strongly encourage you to do the even-numbered ones and to check the answers in the answer key. Number 13. Now on 302 has 2 premises, either not P or Q, either not Q or R. The conclusion is if P, then R. This is kind of a fun one. We're going to create our columns. Again, you won't even have to do this due to the crisis. You're going to be doing this electronically, and so I'm already going to give you the graph. But the number of rows, this is an interesting little thing here. The number of rows is determined entirely by the nature of the conclusion. Like I've said a couple of times before, here's the nice thing. The horseshoe has been something of a mysterious foe to us. Now it's a good buddy. The horseshoe suddenly becomes a good buddy. Here's my conclusion. I want the main connective, that horseshoe, to be false. Question, how many different ways can a horseshoe be false? Just one way. That means we're only going to need 1 row. That's already being a friend. Here's something even more friendly. It's going to give us 2 values right away. If that horseshoe has to be false, the P must be true and the R must be false, because that's the only way for the horseshoe to be false. So if this is a detective story, this is like a witness who's talking a lot. He's given us a lot of information. He's already told us P and R. Okay, where do I go next? Answer, almost anywhere. You could start almost anywhere over here in the premises. There is no one right place. I need to emphasize that. But in order to make this less of a possibility of failure, what I encourage you to do is go to the main connective of the first premise and set it to be true. That way you don't forget that it needs to be true. Now we can put in some values over here. We don't know the value of Q. If you don't know, don't put anything. Never, ever just stick something in because it's empty. We do know P, though. From the conclusion, we know P has to be true. But wait a minute. Thinking like a detective, if P is true, not P must be false. And again, thinking deductively, if that wedge is true and the left side is false, that forces the right side to be true. So now we've determined that Q is true when we hadn't been told anything about it in the conclusion. I think this has surely occurred to you by now. You really need to be able to calculate with the connectives. You cannot do this thinking backwards until you've learned how to do it forwards in a masterful fashion. But this will also help to cement that skill. Now let's go to the second premise. Here again, we could start with Q. We could start with R. We could start with the main connective. There's no one right way, but I do encourage you to set that main connective to be true, because otherwise you could forget. Now, just a second ago, we had deduced that Q is true. So let's stick in T for Q. But wait a minute, if Q is true, not Q must be false, surely. And if the wedge is true, but the left side is false, that means the right side absolutely has got to be true. But wait a minute, we said in the conclusion that R has to be false. So R has to be true and false at the same time. What that means is I cannot consistently assign truth values, making all of the premises true and the conclusion false. I cannot prove that it's invalid, so I've indirectly proved that it's valid. And by the way, this is, since we've got 3 letters now, we are going from a truth table that would be quite large to just a teeny tiny, elegant, beautiful, quick little solution. Okay, enough of that sermon. Let's go and try another one. 15. Now this one looks more challenging. It's not. And once you learn this technique, it's actually fun. So I want you to get to the point where you're actually enjoying it. Here the first premise is not both P and not Q. The second premise is not R implies not P. And the conclusion is if Q, then R. Okay, this is going to require a lot more columns. But if you're looking ahead, I think you'll be pleasantly surprised or pleased. How many rows do we need? It's determined entirely by the nature of the conclusion. And again, we've got a horseshoe, and it's turned out to be our buddy. We finally like the horseshoe. We want that conclusion to be false, so we're going to set the horseshoe to be false. And question, how many ways can a horseshoe be false? Answer, just one. That means we're just going to need one row. How could that horseshoe be false? Well, if the Q is true and the R is false. That's the only way. But again, it's like a witness in a detective whodunit story talking a lot. He's given us a lot of information. Now, we could proceed anyway. You may decide on your own way, more power to you. But if you want a foolproof method, I'm going to encourage you to always go left to right, go to the first premise, find the main connective. That's the tilde here, and set that guy to be true. Now we can reason backwards. If that tilde is true, the main connective inside of the parens has to be the opposite, or false. Now, we don't know anything about P from the conclusion, but in the conclusion, we learn that Q has to be true. So we'll put true for Q, and if Q is true, that means not Q, surely has to be false. Now what we need to notice is, if that tilde is false, the dot is false, and I don't have to say anything about P. If you don't have to say anything about a letter, don't. Or as I put it in the textbook, don't overcommit. If you don't have to commit to say that's definitely got to be a truth value, leave it blank. Blank does not mean you're going to get it wrong. Blank means you didn't have to put anything there. Okay, now let's go to the second premise. The main connective here is the horseshoe. So we want to set it to be true. And we could proceed with the R here. R, we know from the conclusion, needs to be false again. Okay, well, if R is false, that means not R surely has to be true. And if we're thinking like Sherlock Holmes, we realize, well, if that horseshoe is true and the antecedent is true, that forces the consequent to be true. Not P has to be true. But if not P is true, that means P has to be false. Let's check it. Did we have another P? Yeah, right there. But we didn't have to say anything about it. So there's no contradiction here. We could put that F over here, but it's better still. Leave it blank. What this shows then is I can consistently assign truth values, making all the premises true, but the conclusion false. That fits our definition of invalid. I've shown that this argument is invalid. I'm done, and that's the solution, and this shows the exact truth values of each letter that would be required to invalidate that argument. Notice here again, this would be 8 rows. In the other method, this would be 8 rows with all these columns. We've reduced it from 8 to 1 row, and not even a full row. So that's a beautiful thing, if there's any beauty in logic. We're getting into only slightly taller graphs now on page 304. And I can tell you already that I've thrown all the tricks at you that I can. I can make these longer, but I can't make them any more difficult than you've already seen. So if you're good with this at this point, you're doing great. And if not, there's plenty of chance to catch up. Let's look at 17. There's only one premise, both not W and X. The conclusion is it's not the case that W if and only if X. Okay. We're going to take the argument here, create columns like you're surely used to by now. Here we have to ask, now how many rows do I need? We can't tell that right away by the tilde, but we know that the tilde needs to be false. Since the tilde is false, the triple bar has to be what? True. Question, how many different ways can a triple bar be true? Answer, 2 ways. So we're going to have 2 rows. We may not need both of them, but that triple bar can be true 2 different ways. This is actually really rather confusing for a lot of people because what they want to do is to set the triple bar to be false. No, we set the tilde, the main connective, to be false, and that means that the triple bar has to be true. How can that triple bar be true? If it's true, true, or false, false for the simple statements. We're already through most of the process here. We're already mostly done with this problem. Let's go to the first line in the first premise. The main connective is the dot. Set that guy to be true. Okay, if the dot is true, thinking backwards, that means the left side as a whole must be true, meaning the tilde has to be true, and the x has to be true. If not W is true, W had better be false. But what did we say W was in the conclusion? True. So that we got a contradiction here in the sequence that I used. You may use a different sequence and get it somewhere else, but you had better have a contradiction somewhere in that premise on the first line. What that means is the first line isn't going to help me, but maybe the second line will invalidate it, so I have to keep going. I can't stop here and say, it's valid, I have to keep going. Let's go to the second line now in the premise. We want the dot to be true. Let's set that to be true. That would mean that the tilde has to be true. And if not W is true, W has got to be false. And the X here would also have to be true. Now, did we say before that the W is false? Yes, so we're good there. What about the X? We said earlier the X has to be false. So we've got a contradiction here. If you did it in a different sequence, your contradiction will be located elsewhere. But in any case, you'll have a contradiction on that row. What that means is that there is no row, there is no possible combination of truth values where we could consistently assign the premises to be true and the conclusion to be false. We cannot show that it's invalid, so we've indirectly shown it's valid. Okay, again, what we would be doing here would be basically going from 4 rows down to 2. But that's still a nice savings. Let's try number 19. This one looks deceptively simple. One premise, it's not the case that D is a necessary and sufficient condition for E. Therefore, the conclusion is it's not the case that D implies E. What the heck is going on here? What we want to do, and this is number 19, I should have put that up. What we want to do here now is to create a truth table like before. You know how to do the columns. And then the number of rows will be determined by the nature of the conclusion. Here, it's a negated compound proposition, so the tilde alone won't tell us. But we know that we want the tilde to be false, and so that means the horseshoe must be true. Question, how many different ways can a horseshoe be true? Answer, 3 different ways. So we're going to need 3 rows. Hopefully we won't need to use them all, but we're going to create 3 rows with that tilde being false and the horseshoe being true in 3 different ways. How could it be true? If it were true horseshoe true, or false horseshoe true, or false horseshoe false. Those are the 3 combinations. Hopefully we won't have to use them all. Let's just take it 1 row at a time. Now looking at the sole premise here, we see the main connective is that tilde. So we want to set that to be true and not forget about it. Here already we could start by filling in the D and going to the right, or filling in the E and going to the left, or filling in the triple bar and going both ways. It doesn't matter. But since we have already assigned the tilde to be true, it would be most efficient, I think, to then say, I need to remember that the triple bar has to be false, and put an F in there. Now we go to the conclusion. We saw in the conclusion D needs to be true and E needs to be true. Wait a minute. True, triple bar true would make this triple bar true, but it's already false. So we could have the contradiction there. Or we could say, let's let the D be true, the triple bar be false, and the E have the contradiction. Or we could say, let's let E be true, the triple bar be false, and let the D have the contradiction. In other words, you can put it anywhere you want, but you got to have it somewhere. Given my line of reasoning, I think it'd be best to make E true and false. What that means is this row is not going to help me. So I go to the next row. Here I'm going to set the main connective to be true. That means that the triple bar needs to be false again. Now on this row, D is false and E is true. Would that make the triple bar false? Yes, it would. It would make the triple bar false and hence the tilde true. What does that mean? Looking on this second row, I was able to consistently assign truth values, making all of the premises true, but the conclusion false. I can stop there. I've got a row without a contradiction. I can stop there and say that this argument is invalid, and the second row shows me the truth values of the letters where the argument is invalidated. Do I have to do the third row? No, because I've got a row without a contradiction. Again, that chart is going to help emphasize that. So here's an example where you had multiple rows set up, but you didn't have to use them all. Oh, in class, live, so to speak, we normally do 21. But I'm going to skip that one, and because it takes a long time to do, and I won't give you something like that on a test. So let's instead go to 22. This one's sort of fun. What we have in 22 are 2 premises. Not J implies B. If B, then not H. And the conclusion is not both H and not J. This is going to have a fair amount of columns. How many rows will it need? Let's look at the nature of the conclusion. Look, the conclusion has as its main connective this tilde. We need that main connective to be false. So, Sherlock, what does that mean the dot has to be? Right, true. Oh my goodness, now you see it, probably. If that dot is true, what does the H have to be? True. And what does the tilde have to be? True. And if not J is true, J has to be false. There's only one way that the conclusion can be false. Just one way, so we only need one row. Let's go to the first premise. Again, I strongly encourage you to set the main connective to be true. Do we know anything about B? No. Do we know anything about J? Yes. From the conclusion, we know that J needs to be false. Okay, reasoning backwards. If J is false, not J surely has to be true. Okay, reasoning further backwards, if this horseshoe is true and the antecedent is true, what does that force the consequent to be? The consequent B has to be true. If it were F, then it would be true, horseshoe false, and that would make the horseshoe false. But the horseshoe is true, so we need B to be true. Now we've made the first premise true. We have verified or made the first premise true. We've only got one more premise to go. Let's go to the main connective, the horseshoe, and set it to be true. We found out seconds ago that B is true. Let's go ahead and stick that in right away. And we know from the conclusion that H has to be true, so we'll insert that. And if H is true, not H, surely has to be false. But look, if we have true, horseshoe, false, that means the horseshoe has to be false. So it has to be true and false at the same time, a contradiction. What that shows is I cannot consistently assign truth values, making all of the premises true and the conclusion false. Or putting it in more plain English, on every row, and here there's only one, but on every row I've got a contradiction. What that means is it's valid because I can't prove that it's invalid. If it's not invalid, it's valid. Okay, now we're going to go to some different looking kind of practice problems, but these are fun and they go actually quicker than any of the ones we've seen before. But these will be fun, and we've only got 1, 2, 3 more to go. Okay, let's try number 23. I'm going to put this one over here. The reason why it's different is, oh my gosh, it's got 3 premises. You've never seen a practice problem with 3 premises. No big deal. Let's put them down. W implies X. X implies Y. Y implies W. The conclusion is either W or Y. Okay. We'll set up the columns like so. How many rows will we need? Well, again, it depends on the nature of the conclusion. We haven't seen a conclusion yet that's a wedge statement. So we have to ask ourselves, how many different ways can a wedge statement be false? Answer, just one, so that tells us we just need one row. We need the conclusion, the wedge statement, to be false. But the only way that a wedge statement is false is if both disjuncts are false. So it's also like a witness that's talking a lot. It's given us a lot of information. So we know W and Y both need to be false. Here we've got a huge amount of places we could begin. In general, in logic, it's a good principle to follow the trail of the letters. And the only premise where we've got a W and a Y is this third premise. So in one sense, it would be best to start here. But I've taught you to go to the first premise, so let's continue with that method. The first premise, the main connective, is the wedge. We want it to be true. We'll set it to be true. Now here, W is false. We'll put that in. If the antecedent of this horseshoe statement is false, does it matter what the X is? If the X was false, the statement would be true. If X were true, the statement would be true. So it doesn't matter what X is. So don't put anything. Don't overcommit. Leave it blank. Let's go to the second premise. The main connective here is the horseshoe. We want to set it to be true. Do we know anything about X yet? No. Do we know anything about Y? Yes. From the conclusion, we know that Y needs to be false. But think about it, detectives. If we want the horseshoe to be true and the consequent is false, what does that force the antecedent to be? Right. It forces it to be false. So now we know that X is false. Question. Can I go back and put false here? Yeah. Question. Do I have to? No. You can leave this blank forever, but you got to have the F here. We go to the final premise, and its main connective is the horseshoe. We learned just a second ago that Y needs to be false. Let's put that in. W is false, and we want the horseshoe to be true. Does false, horseshoe, false give you a true horseshoe? Yes, it does. No contradiction, and we're done. No contradiction. We've shown we can consistently assign truth values, making all of the premises true but the conclusion false. That fits our classic definition of invalid. And so the argument's invalid and we're done. Notice here, this would have been 16 rows with all of the columns. We have radically narrowed down or minimized the number of T's and F's that we need. Okay, you know what? 25 is a real doozy, and I am hesitant in this format to go through that. What I'd like to do instead is to go to 24. I can tell you that there will be nothing on a test that involves the glitch in 25, but it just simply takes way too long in this format to do number 25. So we're going to go to 24. Now this thing looks evil because it has 4 premises, but it's going to be rather simple and maybe even fun. A, if and only if, either B or C. B implies C. C implies A. And either A or B. The conclusion is A implies B. This has 4 premises, but in principle, we don't do it any differently. You can see here how, oh my goodness, we would have a whole lot of columns And we do. But what about the number of rows? Now, the number of rows here, again, is determined strictly by the nature of the conclusion. And it is our buddy, the horseshoe. We want that horseshoe to be false. How many different ways can a horseshoe be false? Just one. So we're going to have just one row. For the horseshoe to be false, we need the A to be true and the B to be false. That gives us a great deal. Let's go to the first premise. The main connective is the triple bar, so we'll set it to be true. And we know from the conclusion that A is true. So if the triple bar is true and the left equivalent is true, that means the right equivalent as a whole must be true. That would be the wedge. So we'll mark the wedge as true. We know from the conclusion that B is false. But look, if that wedge needs to be true and B is false, that forces C to be true. So we'll make C true, and that will make that entire premise true. Okay, let's go to the second premise. Its main connective is the horseshoe. We'll set it to be true. We just got here a minute ago that B is false. Question: if that antecedent is false, does it matter what C is? No, it doesn't. We learned here a minute ago C is true. We can plug that in, okay, but false horseshoe true will make that horseshoe true. We're good on that premise. We're really cooking now. Let's go to the third premise. C implies A. The horseshoe is the main connective. We want it to be true. We've said that C is true. Plug that in. We've said A is true already. Does true horseshoe true give you a true horseshoe? Yes, it does. So we've verified or made true that premise. Let's go to the last one. The wedge is the main connective. We want it to be true. We've said that A is true, so at least one of the disjuncts is true, making the wedge true. We're done. No contradiction. If there's no contradiction, we can consistently assign truth values, making all the premises true and the conclusion false, which is our classic definition of invalid. And that's that. The last one. This will be number 27. I declare this as the gold standard problem. In other words, if you can do 27, you're in an outstanding situation. Sure, do the ones after that. More power to you. But if you can do 27, that is what I would consider to be the gold standard. Let's do this guy as the last official problem of the semester. This has got a longer set of premises, I'll grant you that. Z implies not K, and A implies not L. Second premise, Z and A. Conclusion, it's not the case that K or L. There are 4 simple statements in this problem. That means you would need, in the usual technique, 16 rows. Now here, how many rows will you need? The main connective is the tilde. We want it to be false, but we don't know how many ways it can be false. Instead, we have to see that the wedge is going to have to be true, because it's the opposite of the tilde. How many different ways can a tilde be, or a wedge rather, be true? 3. So we're going to have to set up 3 rows. We may not need them all, but we have to set up 3 rows. We'll just see how it goes from here. Okay, now, how could this wedge be true? If they were both true, or if K were true and L is false, or if K is false and L is true. There's your 3 ways. Let's go back to the first premise on the first row, and notice again, this is another advantage of the technique I'm teaching, to go to the main connective, the dot, set it to be true. If you do that, what you should realize is, oh my goodness, both of those horseshoes have to be true. Gives you more information right there. Now, what do we know in this first set of fences? We know K needs to be true, which means not K needs to be false. Oh my goodness. If that horseshoe needs to be true and the consequent is false, that means the antecedent absolutely has to be false. Z has to be false. Okay, going over to the second set of parens, we don't know anything about A yet, but from the conclusion we know that L needs to be true. That means that not L needs to be false. But if this horseshoe needs to be true and the consequent false, that means the antecedent needs to be false. A needs to be false. That makes the first premise true, and that was a lot of work, but it's going to quickly help us. Over here, the dot in the second premise is the main connective, so we'll set it to be true. We said, though, that Z is false. So that means that that dot needs to be true and false at the same time. Or we could add the contradiction there, it doesn't matter. But what that shows is that first row is not going to help us. I have to keep going, but maybe it'll get easier. On the second row now, we're going to go to the first premise, the main connective, and set it to be true, which again means that both of those horseshoes need to be true. We're getting good information from that dot being true. On this row, what we've said is that the K needs to be true, which means not K has to be false. And if the horseshoe has to be true, but the consequent false, the antecedent has to be false, so Z has to be false here. Going over here now, we don't know anything about A, but we know L needs to be false. So not L would have to be true. That means we don't have to say anything about A, because if it were either true or false, the horseshoe would still be true. Leave it blank. So that has validated the first premise. Now let's go over to the second premise. We want the main connective dot to be true. That means that the Z will have to be true. But we said previously on this row that Z has to be false. So it has to be true and false at the same time. Bummer, this row won't help us either. But maybe the final row will help. Here, we're going to go again to the first premise, the main connective, and set it to be true, which means both of the horseshoes are true. On this row, K is false this time, which means not K is true, which means we don't have to say anything about Z, because whether Z's true or false will still make the horseshoe true. Oh my gosh, this is turning out a little bit differently. Going over here, we don't know anything about A, but we know that the L has to be true, which would make not L false. Now, if this horseshoe is true and the consequent false, that forces the antecedent A to be false. We know it's got to be false. Well, that validates, or rather verifies, the first premise, but we've still got the second premise to go. We want the dot to be true, which means Z has to be true. Do we say anything about Z? No. So Z can be true. We're right down to the very last second. This whole problem comes down to this cell. If the dot's true, that means A has to be true. What did we say about A before? Oh, that it was false. So the A has to be true and false at the same time. So I've got a contradiction on every row. What that means is I cannot consistently assign truth values, making all the premises true and the conclusion false. I can't prove it's invalid, so I've indirectly shown that it's valid. That concludes all of the practice problems for 3.5, although I encourage you to do the harder ones again. Congratulations on getting this far in the course, and good luck on the final.